The Fourier transform is an important engineering tool. You see its application in many fields. For example, wireless communication uses both Wi-Fi cellular 4 and 5G to shape the data so that they can minimize bandwidth. Audio compression algorithms, they use the Fourier transform to determine what data to remove so they can reduce file size without impacting the audio quality. And in ultrasound, the Fourier transform is used in a variety of applications, but I'm going to highlight one: waveform design. For this talk, I'm going to show how this narrow time domain ultrasound pulse, which is traditionally generated by large, high-powered device, can use the Fourier transform to generate a low amplitude waveform created by a small device. Now for the rest of the talk, I'm going to refer to a narrow pulse as an impulse, since it approximates an impulse and the terminology is useful when applying the Fourier transform. But before we get into the use of the Fourier transform, let's discuss some of the principles of ultrasound. So, ultrasound is used for a wide range of applications in diagnostics, control, and testing. For example, ultrasound is used in industry to measure fluid flow and locate defects. In the medical field, it is used to diagnose heart and liver disease. It can measure muscle position, which can be used to control prosthetic devices for people with limb loss. To do all of this, ultrasound systems measure the change in the acoustical impedance of materials. Here's a cartoon illustrating the process. So this black symbol represents an ultrasound transducer which both sends and receives sound energy. An impulse of sound is transmitted by the transducer, and when it strikes an object, some of its energy will be transmitted and some of it will be reflected back depending on the acoustical impedance difference between this object and the medium that the sound energy was traveling through. Now, if we know the speed of sound in the medium, we can compute the range of this object based on the time it takes for this pulse to have come back and been received by the transducer. And also, if this pulse then strikes another object that has a different acoustical impedance than this object, a second pair of pulses will be generated, and then we can find out the distance of that second object based on the time it takes for the reflected impulse to travel back through the materials and then be received by the transducer. So this allows us to compute the distance to the second object based on the timing of when the transducer receives the pulses. Now, I've described the process using pulses, but why is it that we normally choose an impulse for these applications? So an impulse is a great choice for measuring distances because it doesn't overlap with itself when there's multiple objects, and this contrasts with a sine wave that is added to a delayed copy of itself multiple times depending on how many objects there are. And all these copies interfere constructively and destructively that make distance measurement practically impossible. But what we've learned from the Fourier transform is that sine waves of different frequencies can be separated. And if we can somehow cause the return from each object to be a different frequency, we can then separate those returns and measure the range to each object. But this brings up a question of, well, why don't we just stick with using an impulse? So there are multiple issues with impulses. While impulses are great for precise range measurements, they have multiple disadvantages, and the first of these is that their narrow width means that the transmitter must generate large amplitude pulses in short times. And when you generate large amplitudes, you can introduce nonlinear effects in the medium, which means that your waveform becomes distorted. Also, to generate these large amplitudes, we need amplifiers that can generate high voltages, which are power inefficient and they're dangerous. And while the transmitted impulse is large, what you receive back is small, and to detect these small returns, your receive circuitry must be well shielded not to pick up the transmitted signal by accident. So all of this really adds to the expense and the size of the design. And for the application that we're interested in, of measuring, for example, if interested in measuring muscle motion, you would want a large, low power, low cost system. Therefore, the impulse isn't really the way to go in that application, and so turn to the Fourier transform to help out. So the Fourier transform gives us a playground of sine waves to experiment with. The Fourier transform of an impulse is a set of complex sine waves that span the bandwidth of the system. Now, as a note, in my illustrations, I show just the real components of each of these complex sine waves to simplify the visualization. Additionally, a true impulse contains infinitely many complex sine waves that are each of an infinite length. The impulse I'm using, which is modeling as a narrow pulse, contains only 51 complex sine waves, and each of these are limited in length. Now, because the energy of this impulse is distributed evenly among the sine waves that make it up, the sine waves that compose the impulse are of much lower amplitude, as indicated here by these orange arrows to show the relationship. But this is better illustrated on the next slide. We see here how the impulse is formed, as the low amplitude sine waves, which are shown enlarged in the top, are summed together. The result of this sum is shown in the bottom window, with the relative amplitudes indicated by these orange arrows. Now, as the sine waves are added together, their amplitudes cancel, except in the center where they constructively combine to form the impulse. Now that the Fourier transform has revealed the sine waves that make up the impulse, can we reorganize these sine waves to provide the distance measurement capability of the impulse, but without the high amplitudes and narrow time window that increases the cost and size of the equipment? So if we look at just 3 of the sine waves from our impulse to simplify the visualization, and we recall back when we were talking about why using an impulse to measure the distance to objects, that the problems if we tried to use a sine wave, that we would be able to measure the distance easily between different depths if each return from the different depth was a different frequency. So this inspires us to join these sine waves together end to end so that we can then measure multiple depths with this single long waveform. And this reduces the overall amplitude of the waveform, which is one of our goals, but we need to keep an eye on these abrupt changes because that's going to cause angular discontinuities that we're going to need to deal with later. So the next slide shows what the final waveform looks like when all 51 of these sine waves are joined together. Here we have all 51 sinusoids joined together end to end, and we can compare the relative amplitude with the impulse. From now on, we're going to refer to this joined sinusoid waves as a chirp. and we can see just how much lower in amplitude the joined waveform is compared to this impulse. But we've traded amplitude, a lower amplitude, for time. Now the lower amplitude waveform is much longer in time than the impulse. There's never really a free lunch. But how do these waveforms compare in the frequency domain? If we take the spectrogram of the impulse and chirp, we gain better insight into their relation. Here, the Fourier transform helps us again because the spectrogram is a stacked set of Fourier transforms over time. For the spectrogram, we have frequency increasing vertically and time increasing horizontally. Each vertical column is a separate Fourier transform at a different time. And we see at the moment of the impulse, its Fourier transform spans all frequencies. And if we look at the chirp, we can see that it's just a Fourier transform that's been rotated, of the impulse, that's been rotated 45 degrees, starting at the low frequency and going to the high frequency. And this makes sense because the way we formed the chirp was we started with the low frequency sine wave and we increasingly joined together higher and higher frequency sine waves. Now, in contrast to the impulse, where the frequency content is 0 outside of the narrow time of the impulse, here we can see that there's this leakage of frequency outside of the sine wave's specific frequency. And this results from this abrupt change in angle when we join together the sine waves. Now, if we want to remove this, which we do, we need to explore how the sine waves are generated. And here again, we can use the Fourier transform principles to solve this problem. How do we generate sine waves digitally? Well, we start with an angle, initially, let's say 0 degrees, and we take the sine function of 0 degrees and we get an amplitude, which we use that amplitude value to drive, in our case with ultrasound, a transducer voltage so that we can drive the transducer to a specific voltage. And then we step along and we choose another frequency, another angle. So in this case 45 degrees, take the sine function of that and drive the transducer to the amplitude indicated by the sine function, and we keep doing that with different angles, going all the way up to 360. And the key part to generating a sine wave of a specific frequency digitally is that we do this step with equal size angle increases. In this case, we're using 45 degrees that we add to the previous angle. And so we just keep stepping through that angle every 45, in this case 45 degrees. And if we do this in equally spaced time, then we will have a sine wave of a specific frequency, and that frequency is determined by the step size. So the smaller the step size, the lower the frequency, and the larger the step size, the higher the frequency. And we can see this right here, that if we have a small step size, in this case an angle of 11.25 degrees or pi over 16 radians, that when we do that, we're going to generate in time, we generate a lower frequency if we compare it to a much larger step size, in this case 90 degrees or pi over 2 radians, that we have if over the same time interval we have, in this case, a much lower frequency compared to a much higher frequency, controlled only by the step size. Now, our goal is to be able to go with this chirp waveform from a low frequency to a high frequency without those angle discontinuities. So we can now see what's causing the problem with the angular step, and it's that when we had previously our low frequency sine wave, which was generated by a fixed step of pi over 16 radians in time, and then we had our high frequency sine wave, which was pi over 2 radians of step size in time, that this jump right here is because to go from this point to this point, we had to add pi radians. And so this jump in angle, an angular step, caused that frequency leakage because the derivative of phase is frequency. And so that's causing the problem right here. And what we want to do is we want to smooth this out. We don't want to have a sudden jump in angle. And one way to do this is, instead of adding fixed frequency steps, fixed angular steps, and then suddenly transitioning, is to do a smoother interpolation and just vary the step size over time. And so we're going to vary equally the step size over time. And what this is actually going to cause is that the frequency will smoothly change from a low frequency to a high frequency. So if we focus on changing this frequency, and we look again at that low frequency, and we put some numbers behind this. So we now say, well, the step size will be once every microsecond. So every microsecond, we're going to take a step of pi over 16 radians, which would correspond to a sine wave at 15.6 kilohertz. And if we look at our maximum step of pi over 2 radians, which if we do that, take that step every microsecond, every millionth of a second, that this would result in a sine wave of 125 kilohertz. And if we smoothly interpolate between the two, so we slowly increase that step size, we're going to end up getting this chirp waveform that's smooth without discontinuities. To see this implemented, what we have here is that we've started at the small step size. So once this loops back around, we'll see that when we start at the small step size and slowly increase our step size, what's happening is we're increasing the frequency of the sine wave. So as this red step size increases, which corresponds here to the step size growing in size, that the frequency then will continue to increase. And so this will be our chirp waveform that we'll then use, which doesn't have those discontinuities. So we've shown pictorially how we could implement this algorithm to be able to design a chirp that doesn't have the angle discontinuities, but how would we implement this in a programming language or digitally? And the way we're going to demonstrate this is the use of GNU Radio in the Python programming language, and I'll show you the code, but just to highlight, there's a couple key lines that you want to look for, and these key lines are indicated, these two and then these two down here. And basically what this is actually an array. It looks like one element of an array, but it's pointing to this, what's contained in this 0th element is an array. And so you'll see this, and this array represents a step size of that line that we showed, of increasing this angular delta. So these values are the angular delta in radian, the instantaneous frequency of that chirp at any point in time along that line. And this is just a starting offset, which would represent the, let's say, lowest frequency. And so we form this line that we had previously, and then we sum those angular change in phases, which is what we're doing. These phase values, or these angular values here, are in this array, and when we do this summation in Python using NumPy, what we end up getting are these actual values. And then we take the sign of these actual angular values and we get the actual sine values, which would be the chirp amplitude waveform. And so all we then do, because one of the numerical stability issues that we have in a practical implementation is the wrapping around the circle. So what happens after we've completed that first cycle of the waveform, because as you recall the chirp had multiple cycles in it, that when it wraps back around here, what we need to do is we need to wrap around that phase. And so we do that with this statement down here, and that's all this is. It's just wrapping this back around the unit circle so this angle value doesn't get too big, which can cause stability problems, especially with floating point. So now we want to take the algorithm that we've described to generate the chirp waveform on the slides, and we want to implement it in code. And so using GNU Radio, we're both going to implement the algorithm and visualize it. Now, the implementation, there were basically two parts to that, and they were to generate this diagonal line of increasing angle steps, and that was the steps from 0 to 360 degrees, and the larger the step, the faster, the higher the frequency. And that's going to be done with this block right here. And then we needed to sum those together, those steps together, to figure out what our actual position is, angular position is, in the sine wave, and that's being done right here. And then we're going to visualize the chirp in both time and then the frequency plot. So this part that decides our angular frequency, our instantaneous frequency, which is that step size, is generated. This block here is a sawtooth waveform, so it's going to start at a low value and then go to a high value, which corresponds to our low frequency, and then our high frequency. And then we're going to sum those frequency values, which are our angular step sizes, together in this block, which we wrote in Python. And so if we open this up, we can find the code that we showed on the slide right here to make sure that this is forming that line of the frequency values, which are our angular step sizes, and then we sum those to get our angle that we then feed to the sine function, and we take that and then we output that out of the block. And this code here is just defining that block, what's the input. This is actually the input value from that ramp generator. And we output it, and then we also have to prevent the overflow of the angle from that angle getting too large. What happens after 360? Well, we could keep making it larger and larger, but that causes floating point problems eventually. So instead, what we do is we just wrap it back around to the 360. So that's what the code here is doing. And if we then close that and then play the value, so we can see that here so we have the ramp that's generating the frequencies, and we can see these the chirp changing in time from a low frequency here to a high frequency. Now, one thing we're seeing, because we're dealing with a real signal, not complex, we have positive frequencies, so starting at 0, increasing, and then also negative frequencies. And we can ignore this since this is just a mirror image of the positive frequencies. So if we look at the positive frequencies, we can see when the chirp waveform is of a low frequency here, it's much, the time is, it's a longer period. And then as it increases in frequency, the sine wave becomes compressed. and then it just repeats. So this is a way to generate and then visualize our chirp waveform. When we take our chirp waveform with the smoothly varying frequency, that we no longer have the discontinuities that we had before when we joined together the discrete sine waves. So let's see how to use the waveform to be able to calculate range. Now, if we look at this, break down this diagram, what we have again are these transducers which both send and receive a signal. So that's what this is. This is just the same transducer as this. We're just going to show a waveform in time, and here we're showing the distance to the objects. And what we're going to do is we're going to send our waveform, and because of the acoustical impedance difference between this object and the media, when it hits the waveform interacts with this object, we're going to get a reflection. And then when it goes through here, now for simplicity, I'm not showing the reflection off of the back of this object, and because of this change, so forget about that. But the waveform will travel through, and then when it interacts with this object, we'll get another return on the waveform, or from the waveform, and we'll use those received waveforms to be able to measure the distance to these objects. So let's look at how that's done. So the transducer first transmits our chirp, so we see our chirp starting at the low frequency and going to the high frequency, and it takes this amount of time, and at this time it's traveled this far in distance, so it interacts with this object, and that waveform, the reflected waveform, begins to travel back, but it hasn't yet been received by the transducer. It's received by the transducer at this moment in time. The transducer is going to then start to see this waveform, and during that time, while the waveform was being returning back to the transducer, the waveform's also passing through this object, and then in this time, which happens to just be the same distance from here to here, it doesn't, wouldn't have to be, but just for simplicity, that in this time, once it's just about to be received by the transducer, it also interacts with the second object. And so we see that, so at this time, once the waveform has traveled back to the transducer, which is twice the distance here, because the waveform has to travel out and then be received back, the transducer is now receiving this waveform. So the transducer is both transmitting the chirp, which is going from low to high frequency, and it's receiving a delayed copy of the chirp right here. So it's starting to receive that. And at this moment in time, right here, it begins to receive the delayed copy from the chirp from the object D2. And again, you would have reflections going back this way as the received waveform interacts here if this was a different media, but we're neglecting that for the simplicity of this cartoon. Now, the key part to remember, and this is how range is calculated, the key part to see is that the frequency difference between the delayed copy and the transmitted copy is equal over time. And that's because the slope, those angular steps that we were taking, that increase in angular step is equal for both. Even though this is a low frequency and this is a much higher frequency, the step size is equal. And this is important because we can then measure this difference and then calculate what the distance is. And so we can see that when it starts to receive the waveform from D2, which is the same delayed copy of the transmitted waveform, it has a much higher frequency distance or difference. And this higher frequency difference corresponds to a distance that's farther away. And so there's a linear relationship between this difference in frequency between the transmitted and received and what the distance is. And so that's how we actually measure the difference, or the distance, is by this difference in frequency. And so if you actually look at these waveforms, these combined waveforms, this is what's being added together. So the transducer is both transmitting and receiving, and so this is the copy that you would see, but you can separate this out because of the Fourier transform. We're going to demonstrate this process of transmitting and receiving the waveforms again with GNU Radio. And just to familiarize or to orient you to what we're going to see is that given the previous slide setup, this maps to the GNU Radio demonstration if you take everything and you rotate it by 90 degrees. So in this case, the frequency, which is starting here at 0 and going to some stopping frequency, maps to right here in frequency. So starting at 0, going to some increasing positive frequency. We can neglect this left-hand side of the spectrogram that we're going to see, because in this case we're dealing with real frequencies, and so we get the positive and negative frequencies. So we can neglect this part here, but what we're going to end up seeing is that we're going to end up seeing our transmitted waveform, which corresponds to here, and then we're going to see the delayed copies of D1 of the received waveform, and then D2. Here we're going to demonstrate receiving the chirp waveform, and this is similar to the block diagram. We have similar blocks to when we generated the chirp waveform, but then we're going to add in a couple blocks to simulate two objects at different depths. So again, we have this here is the generation of the chirp. This will be our simulation of the objects, and then this is going to be our analysis of being able to look at the data. And so these are the same as the previous demonstration, but what we've added to be able to simulate the object 1 and object 2 are two delays, because the objects, what they do is they reflect back the waveform we've generated, and we can represent that, we can simulate that by putting a specific amount of time. So we have a delay, so basically we generate our chirp here, which instantly goes to this adder block, and then we have a delayed copy which represents the first object. So this would be the time it would take for the chirp when it interacts and is reflected back from that first object to be able to then get back to the transducer. And we also have the second object right here. So this would then be the additional time it takes for the chirp waveform to get to the second object and then be received by the transducer. And so we're going to then see on the display, we'll see the original transmitted waveform and then two delayed copies representing what we're receiving. So if we run this, we can then execute the flow graph, and what we see again is our chirp waveform, but now instead of just that transmitted copy, we also get the delayed copies from object 1 and then object 2, and then we can see that this repeats again. And so we have a way in GNU Radio to take the existing code and to simulate what the transducer would receive if there were two objects equally spaced at equal intervals from the transducer. So in conclusion, we've seen that the Fourier transform really is critical to being able to do this type of waveform design. It's allowed us to go from a waveform that was an impulse with high peak power to a lower power waveform, which can allow us to design lower power ultrasound equipment. And the Fourier transform here not only is useful to design the waveform, but it also provides a way to visualize the waveform. And this isn't the only use of the Fourier transform in ultrasound. There's a lot of other applications, even specifically within this chirped waveform setup. We can use the Fourier transform to transform this received signal into an image. And so that could be a future presentation. And then also, we could use the Fourier transform to take this waveform and measure the velocity of an object that's moving. We had just static objects that weren't moving, but if they were moving, we could use the Fourier transform to do that. And we can use the two-dimensional Fourier transform to measure both the range and velocity of the objects. And so to be able to get the code, if you want to extend the demo or try the demo out for yourself with GNU Radio, you can go to this URL and download it there.